All right, chemistry, let's look at our second video lecture for this combined section. Last section, we introduced chemical bonding in general. Today, we're going to look at covalent bonding specifically. In this section, I want you to be able to explain the relationship of potential energy and distance between approaching atoms, meaning atoms that have not bonded yet, but they're about to. Describe the Octet rule as it applies to ionic and covalent bonding. And then we are going to introduce writing Lewis structures to illustrate ionic and covalent bonds. And then, not quite as much, we're going to write Lewis structures for polyatomic ions and molecules with multiple bonds. So here we go.
A chemical bond is the force of attraction that holds two atoms together. As independent particles, atoms are at a relatively high potential energy. Most atoms are less stable existing by themselves than when they are combined. By bonding with each other, atoms decrease in potential energy, thereby creating more stable arrangements of matter.
All right. Thank you very much, Robot Lady. That essentially is going to be the fulfillment of our first objective, being able to describe the relationship between potential energy and distance between approaching atoms. Here, refer to this video as it in a nutshell. So let's start off with a few different terms. First, let's look at molecule. Molecule is a neutral group of atoms that are held together by covalent bonds. So when we say molecule, we are actually not just saying a group of atoms bonded together. We're saying a group of atoms covalently bonded together. Something like NaCl, sodium chloride, is not a molecule. We have a different name for that. Okay, it's a formula unit because it's ionically bonded. Molecules are covalently bonded. So when we have a molecular compound, it's a chemical compound whose simplest units are molecules, meaning they're covalently bonded. We're going to be learning how to read chemical formulas. Those chemical formulas indicate the number of atoms of each kind in that compound, like H2O is a chemical formula. There are H's there. There are two of them, in fact. And there are O's in there, and there's one of them, H2O. We know what type of element is present and how many. Molecular formula shows the types and numbers of atoms combined in a single molecule of a molecular compound. So if I say the formula of the molecule, it's the molecular formula. It's the chemical formula describing a molecule, meaning something that's covalently bonded as opposed to ionically bonded. To review from last time, the diatomic molecule, it contains only two atoms, and we have a mnemonic. Yeah, that helps us remember the 7 elements that are diatomic in their free state. This means that referring to a sample of oxygen is actually referring to a sample of O2. Okay? Remember, there are 7 elements that form pure non-covalent bonds of Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Now, let's continue to look at a covalent bond. An important aspect of covalent bond is the bond length. Remember, we want to be able to relate bond length and potential energy. So, the distance between two bonded atoms at their minimum potential energy. That is the average distance between two bonded atoms. It's the average distance between two bonded atoms because nature always supports low energy arrangements. So these two atoms are going to find themselves at a distance in which the potential energy is at a minimum. Why? Because nature favors low energy constructions. We also have another aspect of covalent bonds. We call it the bond energy. The bond energy is the amount of energy required to break a chemical bond and form new isolated atoms. And so we're not breaking these bonds to have these atoms participate in a different alternate chemical reaction. We're just resulting, we're creating free atoms. So if we have H2O, we're breaking all the hydrogen-oxygen bonds to have two individual isolated hydrogens and one isolated individual oxygen.
Chemical bonds form when reacting atoms reach a lower potential energy when bonded than those same atoms would have as independent particles. In forming a covalent bond, electrons are shared and energy is released. The same amount of energy is needed to break them apart. This is called the bond energy. Bond energy varies with different kinds of atoms, as shown in this table.
All right, so Robot Lady gave us a little intro into our next question. Why do atoms bond? We want to remember a few things. We want to remember the octet rule, that by gaining, losing, or sharing electrons, each atom is going to have a total of 8 electrons in their outermost energy level, okay? The S and P sublevels, they're valence electrons. Why is that important? Because it results in stability. Atoms have a higher potential energy when they exist alone in nature. Hydrogen has a higher potential energy when it's by itself compared to when it's bonded to another hydrogen. Remember, nature favors arrangements in which potential energy is minimized. This means that most atoms are actually less stable, existing by themselves, compared to when they are combined in some sort of bonding. So remember the octet rule. Chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, has an octet of electrons and its highest occupied energy level, the valence shell. This is the major driving force for why atoms bond. They all want, I have a want in quotations there because they're not sentient. They don't have a personality. They're not desiring this. It's just a natural predisposition towards this. But they all want to be just like the noble gases in terms of their electron configuration, which already have an octet of electrons. Now, there are a couple of exceptions to the octet rule. Boron, for example, only has 3 valence electrons. And since the valence electrons are the electrons that are involved in bonding, boron can only form 3 bonds. Well, once those 3 bonds have been made, the boron atom only has 6 valence electrons, not 8. Well, that's all boron can do. It just happens to be an exception to the octet rule. Now, we also have some expanded octets where we have more than 8 valence electrons. This is where we're going to start to see some silly things that will make sense a little bit if we sit down and think about it for a while, but it's not going to just come naturally to you. So some elements can be surrounded by more than 8 electrons if they combine with highly electronegative elements like fluorine, oxygen, and chlorine. In these cases, it's the d orbital electrons, the d sublevel electrons that are involved in bonding in addition to the s and p orbital electrons, aka the valence electrons. So in addition to this bromine right here having 8 valence electrons, there is an extra set of electrons available. These are d sublevel electrons. However, because these fluorines are so highly electronegative, they are pulling electrons towards themselves. Okay, they can actually draw these d sublevel electrons towards them, only because they are so electronegative. Other elements will not do that. You cannot do that.
The noble gas atoms are the only ones that exist readily in an isolated state in nature. The outer s and p orbitals of these elements are completely filled with electrons, 8 in most cases and 2 in the case of helium. As a result, these atoms have low potential energies and stable electron configurations. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. In this way, each atom has a stable noble gas type structure. Let's look at this same combination of atoms using orbital notation. If we join the unfilled orbitals of 2 atoms with a box, we see that the combination fills the orbital. There are, however, some exceptions to the octet rule. The most important ones relate to the elements hydrogen and boron. Hydrogen forms compounds to share a pair of electrons, filling its s orbital. Boron has only 3 valence electrons, and so forms compounds to share 6 electrons, filling its s and 2p orbitals.
Thank you, Robot Lady. All right, the last thing we're going to do is we're going to introduce the idea of electron-dot notation. An electron-dot notation and electron configuration notation in which only the valence electrons of an atom of a particular element are shown. They're indicated by dots placed around the element symbol. Now, it makes sense that we only represent the valence electrons because if we're going to talk about bonding, which we are, we're in Chapter 6, we're only going to be talking about the valence electrons, because those are the electrons involved in bonding. Now remember, you don't need this table. You can simply look at the main group number and know how many valence electrons a particular element has. But what we do see is how to represent each of these main group elements in electron-dot notation. And this is going to be essential for writing Lewis structures. So what I want us to do now, go ahead and press pause on the video. We're going to write electron-dot notation for each of the following elements. Hopefully do it on your own. If you need to refer to the table, feel free. Press pause now. All right, let's see how we did. How do we do? How do we do? That bad, huh? All right, better next time. Now we're going to use that to draw Lewis structures. Now I have a set of steps for you to follow, and as we practice these, you have to have this set of steps out and available and following it step by step. As we start, you have to have this out while you're working on your drawings. As you move on and become more experienced, you're going to not need this list of steps, but to start, you have to do it. So first, we're going to determine the type and number of atoms in that molecule. Then we're going to write the electron-dot notation for each type of atom in that molecule. We're going to count the total number of valence electrons in the atoms. We're going to arrange the atom to form a skeleton structure of that molecule. Now, if carbon is present, it's always the central atom. That's why carbon is so important. Otherwise, we're going to pick the least electronegative atom. As long as it's not hydrogen, okay, the least electronegative atom will be central. And then we're going to surround that central atom with the other atoms, the leftover atoms, using electron pair bonds. We're going to add unshared pairs of electrons so that each hydrogen atom shares a pair of electrons, and each other nonmetal is surrounded by 8 electrons, trying to satisfy that octet rule. At the end, we're going to count the electrons in the structure to be sure that the number of valence electrons used equals the number available, that number that we counted up in number 3. So we're going to follow along. I'm not going to pause on this one. We are going to draw CH3Br. We're referring to 6 steps on the previous slide. Now here are the 3 elements I'm going to be using. Now there are 3 hydrogens. Okay, so I'm going to start. Oh, we have carbon, so I'm going to put carbon as my central atom. I'm going to surround carbon with the other 4 atoms that I have, 1 bromine and 3 hydrogens, and then place the electron pairs in between the atoms to represent the bonds within the molecule. All right, guys, that's going to do it for this video lecture. I will see you next period.